Machine learning, deep learning, and artificial intelligence are some of the fastest growing areas of computer science and engineering. In this video, I'm going to cover the core concepts of machine learning and write a Python program to demonstrate them. So the key idea behind machine learning is to have computers learn to solve a problem using a set of training data that we provide. So there's lots of kinds of machine learning. There's supervised, unsupervised, reinforcement learning. In this video, I'm going to focus on supervised learning. I think it provides the most intuition on how we drive a machine to adapt from the training data. So in supervised learning, our training data consists of what would be the inputs to our problem and also the desired output for that corresponding input. So, for example, if our data is coordinates in 2D space and the problem is to classify them as either being a part of group 1 or group 2, then the training data will consist of your set of data points in 2D space and also the classification of each data point as being a part of either group 1 or group 2. So then our computer can learn based on this data to classify new data as either group 1 or group 2 using its knowledge of how the training data was correlated. So Perceptron was one of the first algorithms I learned when I was studying machine learning, and I think it's a good way to introduce the concept. So Perceptron is an algorithm that looks to find a linear boundary to separate two groups of data. We can represent our linear boundary. As you can see in the picture on the right, there's a blue decision boundary separating the green data points from the orange data points. That blue line can be represented with a vector that's perpendicular to it. We can call that W. Now, if we project our data along W, since W is perpendicular to the boundary, we can guarantee that anything greater than some threshold amount will be in our orange classification, and less than some threshold amount will be in our green classification. We can also instead take the dot product and then add some bias to remove the threshold and make it 0. So in this case, we add a bias so that if the dot product plus the bias is greater than 0, we're in the orange group, or less than 0, we're in the green group. So now instead of trying to find a linear or a line that separates the data points, we're trying to find the perpendicular vector that projects our data into the one-dimensional space such that anything greater than 0 is a part of the orange group and less than 0 is a part of the green group. And then this last bullet point is just a quick trick we can use to build the bias component into our W vector as the third dimension, and then it's like a homogeneous coordinate system where now we add 1 to the end of our point vector, and if we took the dot product between these, then functionally we're just adding the bias to the original dot product. A key concept in machine learning is to define an error function that represents the amount of error there is in your system at a given time, and then find the derivative of your error function, and you can descend the gradient, the derivative or the slope, whatever you want to call it, to get to the minima of the function. And this way you know you're operating at the optimal solution where the error in your system is minimized. So a common way to write your error function would just be simply what should we get minus what did we get. So in the case of Perceptron, that is the dot product. What we did get, or our current output, is the dot product of our current W with X. The desired output is the ideal output at that situation. So in Perceptron, this error function shouldn't be usable because it implies that we already know the optimal W. But I think this algorithm is important enough where I should teach it anyways. But yeah, just know that this application for Perceptron is kind of useless. Anyways, we want to square our error function to take the slope of a parabolic function, assuming the initial error function is linear, because we want to find the minimum error. So here we could just descend the slope of the parabola, and we're going to want to take the derivative of our error function to get the slope. We know from calculus the derivative of something squared with respect to x is 2 times that something times the derivative of it with respect to x, so in this case w. And so our error function is 2 times the error times negative x. Negative x is essentially our derivative vector, or our gradient vector, because since w is multidimensional, our gradient has 3 partial derivatives for the 3 components of w, and we know from the dot product operator we have a sum of products of first component of w with first component of x. So the partial derivative with respect to each component is the associated component, the negative associated component of x, because there's a minus in front of the dot product. And so negative x is our gradient vector. Essentially, it's our vector of partial derivatives with respect to each component of w. We can then update our w vector with the current w vector, and then we descend our slope, so we subtract the derivative, and since there was a negative in the derivative already, we're adding, where here n represents a learning rate. We usually apply a learning rate for how fast we want to descend the slope of our error function, and then just the slope, 2 times the error times x. So there's a much more complete explanation of the derivation of this function from the guy who actually invented it, and I'll link that video in the description. But at the time, they were doing a statistical approach to this where you were trying to minimize the mean squared error. And in order to minimize the mean squared error, you had to take the expected value of error, which would require you to average the error over every single input training pattern, which was not doable in real time. And if you wanted to train a system in real time as data comes in, you needed an algorithm that could adapt from the current set of data, or the current training case. And so instead of taking the mean squared error in our derivative, they use the error at one instance. And so our gradient isn't the actual gradient to minimize our mean squared error function, but it's an estimate of it at one instance of error. So they call that an instantaneous gradient. Okay, so how can our perceptron algorithm learn to find this w vector and its bias component? We know that least squared error function from the last slide is not really applicable to perceptron. We don't have the optimal w. What we do have is just the label of each training data. So we want to define a metric to determine how wrong our w vector is. We want it to be large when there's a lot of errors and small when there's not a lot of errors. So if we assume our output labels are -1 for group 1, so that means the projection with w was less than 0, and +1 for group 2, meaning our projection was greater than 0, then we can define our error function like this. We know if we multiply our result, which is greater than 0 if we think it should be in group 2, and less than 0 if we think it should be in group 1. And then if we multiply it by the label, if the signs are different, we had a misclassification, and that would result in a negative result. So we negate this entire function, And the more wrong decisions we make, the bigger the value our error function will give us. And so we have an error function that grows with respect to wrong decisions and shrinks the more right decisions we have. So this function is going to kind of look like an absolute value function if we assume that the relationship between changes in W create a linear change in the number of errors seen in the output. So it gives us this sort of V shape, and it's kind of similar to an absolute value function where the amount of error grows when W is smaller and or bigger than the ideal value it should be operating at. And then this is another function where we can just descend the gradient to get to the function minima. So we take the gradient of our function, which the gradient of this function with respect to W is x times the label of x, which is either -1 or +1 for group 1 or group 2. We can update our W vector. And again, this is a gradient vector. The dot product, again, taking the derivative gives us the partial derivative with respect to each component of W. So we can update W on when we receive an error by following the reverse direction of the gradient multiplied by some learning rate, just like we did in the least squared error example. And so the next value of W is going to be W minus our learning rate times the derivative of error with respect to W, which is already negative. So we have W plus n times x times the label of x. And that's how we're going to update W. Okay, so let's do some code to visualize the perceptron algorithm. I'm just going to walk through the setup of the code quickly. So I'm going to have a LMS switch, so I can choose to use either the least squared algorithm or the perceptron algorithm that I showed in the presentation. N will be my number of training datas, and I just have a range of what I'll allow for the two-dimensional data points. So I'll set up a random W vector. This will be my ideal W vector that I'm using to generate the class labels of my data. Then for each data point, I'm going to randomize data within the range. Set it to be group 1, or the label of 1 if it's greater than or equal to 0 when we do the dot product of the W vector we chose, and -1 if it's less than 0. Then if we're using the least mean squared or the least squared algorithm, then we're going to create the training data contains the x, the y for the 2D, the label, and then the actual value of the dot product of W with x, because we need the desired output to perform this algorithm. Otherwise, for normal perceptron, we just need the label as the output. We're going to create, again, a random W vector. So our W vector is going to be wrong at the start, and we're going to adapt it. I'm going to just plot the initial guess at our W vector. And then we're going to get into our while loop, and we're only going to break out once the perceptron algorithm has found a solution. So we're going to get into a for loop. We're going to read through each piece of training data, perform our projection with the W vector. So we'll do that now. So the data is going to be at data point I. We just need the first two values at this data vector, being the x and y component of the 2D point. We're going to make it bring it to the homogeneous coordinate system by appending 1 to the end of it. That's just so the dot product with the W with the bias built in
becomes the dot product of w with x plus the bias. So then our prediction is that dot product. I'm using NumPy. All right, and then we're going to do our cases. So if our prediction is greater than or equal to 0, that means we chose a label of 1. Otherwise, we chose a label of 0, of -1. So if our prediction is wrong, we'll check the label of the data, and then this was the label of our prediction. We have to increment the amount of errors we had. And then we're going to use the two algorithms. So the mean squared algorithm, will first define our error data. This is the third column, or technically the fourth column of data, which was our optimal W projection, so our desired output minus the actual output we had, which was the original prediction, and our W vector is going to be the W vector we currently have plus the gradient of our error, this is seen in my video. Otherwise, for the perceptron algorithm, we just update our W vector with the rate times x times the label. Yes, that should be the whole algorithm, so let's run this. And we can see that green line finding the boundary until we get 0 errors. Yeah, thank you for watching. Please feel free to like, subscribe, and leave a comment.